Circular Economy, Benefits to Cost of Construction in the Nigerian State, a Review. Abstract, this review investigates the concept of circular economy, its benefits to cost within the construction industry in Nigeria. A systematic literature review was conducted focusing on the benefits to cost in a circular economy of the construction industry. The key findings from the review are the three pillars of circular economy: sustainability, economic, environmental, and social benefits, and how they add value directly to the construction industry in the worldwide perspective, and how it can potentially add value to the Nigerian construction industry, when wholly applied and enforced by policymaker, such as the government. The application of the concept of circular economy thinking in construction, which is at its infant stage in most developing countries such as Nigeria, has been mainly limited to construction waste minimization and recycling. Little or no research has been taken on the circular economy from its benefit to cost in the construction industry in Nigeria. The survey results from several literatures and workshops materials were utilized. This paper provides a reviewed analysis on the concept of circular economy, CE, its definition, principles, and benefits to cost in the Nigerian construction industry. It also reviewed the construction industry, construction material waste situation, construction waste recovery systems, and waste management policies in Nigeria. To encourage greater implementation of circular economy principles throughout the supply chain, a clear economic case is paramount, supported by metrics, tools, and guidance, and the support from the government through the regulatory agencies such as COREN, in the case of Nigeria. Keyword: circular economy, CE, construction industry, waste, benefit, Nigeria. 1.0 Introduction. The circular economy, CE, contributes to raising productivity, optimizing the use of natural and human resources, CENIM, 2019, Miss Emmer, 2018, and increasing efficiency in resource management, CENIM, 2019, Linder and Williander, 2017, EA, 2016. CE proposes to replace wasteful and inefficient linear and open-ended cycles of production, input-output waste, for a closed loop where waste is minimized or transformed into inputs and value is created in the process, CENIM, 2019, Homrich et al., 2018, Blomsma and Brennan, 2017. CE ideas have been gaining traction in the past decade in policy formulation, advocacy, consulting and natural sciences, CENIM, 2019, Riakit et al., 2018. The concept has been accepted by businesses across different sectors around the world as a solution to promote sustainability. Osabajo et al., 2020, Gazellanyet et al., 2018, Leader and Rashid, 2016, Preston, 2012, and the construction industry is not an exception. The construction industry is said to produce more waste than any other industrial sector. Osabajo et al., 2020, Rose and Steegman, 2018. It's from the fact that the construction industry is a major exploiter of natural non-renewable resources and a polluter of the environment. Construction activity contributes to environmental degradation through resource depletion, land use and deterioration, power consumption, air pollution, and the generation of waste in the acquisition of raw materials. Sedu, 2016, Tam, 2008, Danya et al., 2007. The majority of this waste has not been well managed, thus causing substantial health and environmental problems. Sedu, 2016, Imam et al., 2008, and affecting the performance of many projects in Nigeria. Sedu, 2016, Atiwurcha and Otala, 2013, Omale and Idido, 2013, Oladaran, 2009. Despite the vast amount of waste from construction activities, Osabajo et al., 2020, Bilal et al., 2016, Clark et al., 2006, and significant impacts of the construction industry on the environment, society, and economy, Onyowoicho al. 2020, Genslet al. 2012. Limited studies have been conducted on CE application within the construction industry, Onyowoicho al. 2020, Leader and Rashid, 2016. Studies, Tucker, 2015, Pan et al., 2015, suggested the need to explore strategies to convert and/or recover the industrial waste for recycling and reuse. This idea is consistent with Smollett al. 2015, views, who argued that the construction sector could benefit maximally from CE. Other studies clamoring for sustainability in the construction industry, Onyowoicho al. 2020, Gazelanyet al. 2018, Kailalai and Fokides, 2017, Lai et al. 2017, Lehman et al. 2011, have highlighted the importance of CE in this process. These studies seek to explore the efficacy of CE, understanding its cost and benefits in the construction industry, and to understand the extent to best apply the principles of CE in the construction activities. Therefore, strategic explorations for the acceleration of Nigeria construction industry transition from the traditional linear economy, LE, to CE should be the center of interest for current and further researches. One such strategy is to identify the extent of research coverage on the cost and benefits of CE implementation in the construction industry from existing literature. Thus, this study systematically analyzes literature surrounding cost and benefits of CE in the construction industry. Circular economy. The term circular economy is becoming increasingly commonplace. Countries such as China and Germany have used the term within their legislation, although the emphasis can vary. Adams et al., 2017, Benton, 2015. Waste avoidance and closed-loop recycling are the key components within the German legislation, Adams et al., 2017, Bilituski, 2012, while in the Chinese policy, the term is directed at eco-design, cleaner production and eco-industrial parks and networks to create a recycling-oriented society, Adams et al., 2017, Gen et al., 2012. The concept circular economy, CE, has drawn considerable attention among researchers, institutions, and policymakers. It is geared towards innovative and regenerative resource consumption, which is different from the usual linear model. Ogakwu et al., 2020, Eziefula and Eziefula, 2019. Linear economy, LE, evolved from Industrial Revolution, as products follow the process of resource extraction, manufacture, distribution, marketing, consumption, repair/reuse, disposal, waste. Ogakwu et al., 2020, Salguero et al., 2019. Linear economy is shown in Figure 1b below. However, the CE model promotes the concept that a product that has been perceived to have reached its end of life in a particular system might be used as a raw material in another or the same system, as shown in Figure 1a. The circularity principle further reframes the traditional viewpoint by considering waste products as resources that could have an endless or multiple lifespan with economic, social, and environmental gains. Tunt, 2019, Plastinen et al., 2019. Since the first formal use of the circular economy term by Pierce and Turner, 1990, there have been various attempts to define the circular economy influenced by several concepts. A number of authors have provided resource-oriented definitions and/or interpretations, emphasizing the need to create closed loops of material flows and reduce the consumption of virgin resources and its attendant harmful environmental impacts. For instance, Kircher et al., 2017, defined CE as an approach to replacing the end-of-life concept with an economic system that fosters reuse, alternatively reducing, recovering and recycling of materials in distribution/production and consumption processes. Geisdorf et al., 2017, describes CE as a regenerative process, which maximizes the utilization of raw materials and reduces emissions and waste generation through repair, remanufacture, reuse, recycling and refurbishing. Also, SAVA A copyright ETAL, 2016, suggests that the circular economy refers to the production and consumption of goods through closed-loop material flows that internalize environmental externalities linked to virgin resource extraction and the generation of waste, including pollution. In their view, the primary focus of the circular economy is the reduction of resource consumption, pollution, and waste in each step of the life cycle of the product. There is also a consensus that it promotes longer life cycle of components, materials, and products through reuse, repair, recycling, remanufacture and refurbishing, ZACO ETAL, 2018. History of circular economy concept. When investigating how the concept of circular economy arose and where it originates from, it is interesting to see that circular economy is inspired by different authors and influenced by several theories. However, several studies point at David Pearce and Carrie Turner as the founders of the conceptual framework for circular economy, Svensson and Tang, 2018. Wijnandseth al., 2017, Geisdorferet al., 2016, Suet al., 2013. Even though Geisdorfer et al., 2016, elaborated that the concept of circular economy has gained attention by authors since the late 1970s, and since then gained political awareness. The global attention to the term is not as popular as the term sustainability. Circular economy has its roots in several concepts such as general system theory, cradle-to-cradle, laws of ecology, looped and performance economy, regenerative design, industrial ecology, industrial symbiosis, ecocity, biomimicry, and the blue economy, all of which touch upon the idea of closing the loop. Svensson and Tang, 2018, Wijnandseth al., 2017, Geisdorferet al., 2016, Gazellignet al., 2015. The different theories have all affected and influenced circular economy in how it is perceived today. In an attempt to change the linear economy, Pearce and Turner's idea of circular economy is to attach the ends of the linear economy resulting in a loop. The loop is used to describe the industrial strategies for waste prevention, resource efficiency, and dematerialization of the industrial economy. Svensson and Tang, 2018, Geisdorfer et al., 2016. Furthermore, Pearce and Turner conceptualize circular economy with 3 Rs: A reduce, reuse, and recycle. Source: Svensson and Tang, 2018. Reduce refers to reduction of raw materials and the use of polluting energy resources as the primary energy. Reuse refers to the reuse of products and byproducts, as well as handling waste as a resource. Lastly, recycle refers to producing products with recyclable materials, which also reduces the extraction of virgin materials. Other studies have supplemented the 3 Rs with recover, remanufacture, redesign, refurbish, repair, and the newest R from Advisory Board A rethink. There is no doubt that all Rs promote a wish for closing the loop. In Figure 3, the content of each word is described. However, some of these terms can have the same meanings as other Rs and some are identified as broad categories, e.g. redesign and rethink. Figure 3. Circular economy in the construction industry. The current view suggests that it is likely impossible to reuse materials within the construction industry, considering that buildings are often disposed of at the end of their useful life. For example, demolition and construction waste in the United Kingdom is at an annual average of 45.8 million tons, Akon by et al., 2018. In response to Nunez Cacho et al., 2018, observation that the construction industry requires a closer attention due to its environmental impact, the industry should improve its resource consumption, Smollett al., 2015. The current trends and practices in the construction industry suggest that CE can facilitate the sustainability of the industry. The starting point is to understand how CE could contribute to the construction industry, given that CE can be instrumental in reducing the environmental impact of the construction activities. Gazelani et al., 2018. This is in line with Van Stein and Gru's, 2019, assertion that the transition to a circular economy in the built environment is key to achieving a resource-effective society. As a result, this study is designed to assess the current research focus on the cost and benefits of CE in the construction industry in Nigeria. Study area, Nigeria. Nigeria is located in West Africa. The total land area of Nigeria is 910,770 square kilometers, while water bodies accounts for 13,000 square kilometers. The population of Nigeria has been approximated at 198 million people as of 2018, calculated with 3.2% annual population growth index and also based on the 2006 population census figure of 140,431,790, PRB, 2018. Nigeria accounts for 2.6% of global population. It is the seventh most populous country of the world, Ogakwu et al., 2020, NNPC, 2019. 36 states and a federal capital territory, Abuja, make up the country. The country is characterized with a very young population. The average age of the population is 17.9 years, Ogakwu et al., 2020, Olaniyan et al., 2018. The country has enormous prospects, specifically in the areas of natural resources and human capital potential. It has a great endowment in crude oil and natural gas, solid minerals, vast and suitable land for agriculture and water and forest resources. Tund, 2019, Eziefula et al., 2019. However, the country's rich endowment in natural resources somehow has facilitated enormous economic prosperity, such that it has been consistently rated among the largest economies in sub-Sahara Africa since 2004. But Nigeria is currently contending with enormous social-economic challenges, such as a high unemployment index, technological backwardness, an underdeveloped agricultural sector and per capita poverty index. Hence, Nigeria was recently rated the poverty capital of the world, Adibia, 2018. The National Bureau of Statistics, NBS, recently released the 2019 Poverty and Inequality in Nigeria report, which highlights that 40% of the total population, almost 83 million, live below the country's poverty line of 137,430 naira, $381.75, per year. Brief overview of waste management policies in Nigeria. Solid waste management in Nigeria came with the establishment of the Federal Environmental Protection Agency, FEPA, in 1988, Abala and Kantala, 2013. The FEPA was later merged with other key government agencies to form the Federal Ministry of Environment in 1999. The responsibility of this ministry is to issue guidelines on how key environmental issues, including solid waste management, should be tackled. However, the task of making laws, implementations, and enforcement mostly lie on the state governments through various state ministries of the environment and municipal councils. The guideline on solid waste management in the country was released in 2005 by the Federal Ministry of Environment. The policy document recognized the fact that strategies for waste management at the grassroots level should interface with the local culture, land use type, economic base, climatic condition, existing urbanization level and institutional arrangements, EPHW, 2005. The guideline, however, was no detailed on each aspect of solid waste management, such as waste reuse, recycling, and final disposal techniques. Despite the high levels of material waste, WAHB and Lawal, 2011, observed that little attention is given to construction waste in Nigeria and argued that a low means of disposal and the lack of awareness may be responsible. In support of their observation, Karim et al., 2015, further explained that the high volume of wastes is due to the availability of inexpensive disposal methods, suggesting the need for government regulatory policies and organizational policies. According to the Lagos State Waste Management Authority, LAMA, 2014, there are 5 landfill sites, 3 major sites and 2 temporary sites, in the state, where all types of waste, including construction, are disposed. The recycling of construction waste in Lagos has been described to be very low. Onyowoicho al., 2019, Igbenamwanhaya, 2011, while some household wastes, such as plastics and papers, are recycled to some extent. Onyowoicho al., 2019, Lama, 2014. Construction material waste situation in Nigeria. Material wastage has become a serious problem, which requires urgent attention in the Nigerian construction industry. This constraint harmfully affects the delivery of many projects. Atiwurcha, 2013. Teo et al., 2009, observed that extra construction materials are usually purchased due to material wastage during the construction process. Atiwurcha, 2013, argue that despite the 5% allowance made to take care of material wastage in the course of preparing, an estimate for a project is usually inadequate, because there is a lot more waste generated by construction projects in Nigeria. Babatunde, 2012, emphasizes that the problem of construction material waste is well known in Nigeria, but it seems not to be given the recognition or the attention it deserves. Most of the material waste is sent to landfills without considering its economic importance, through recycling or reprocessing into new products. This would reduce the burden on the landfill, as well as the environmental effects. Wahab and Lawal, 2011. The factors contributing significantly to construction material wastage in the rivers state of Nigeria, as outlined by Atiwurcha, 2013, are rework as a result of non-compliance with drawings and specifications, variation and modification in design, and waste from inefficient and wasteful shapes, respectively. Insufficient construction materials waste was rated least among the factors. Atiwurcha, 2013, highlighted the fact that contractors and consultants have the same insight on the factors causing construction waste generation in the Delta state of Nigeria. In the view of Omale and IJERT, 2013, poor supervision of construction workers is the major factor contributing to material wastage in the Nigerian construction industry. Wastage of material is common in construction projects in Nigeria, and this is as a result of several sources and causes. These occurrences pose a lot of challenges and have negative implications for the stakeholders in the form of high transportation cost to landfills and so on. The identification of these causes and the application of relevant control techniques to minimize their occurrence could be a step towards alleviating the consequences. Oladaran, 2009. Construction waste recovery systems, reuse and recycling. The recovery of construction waste, according to the United States Environmental Protection Agency, USPA, 2000, encompasses the choice of the material to be recovered, which depends on factors, such as the type of project, on-site space, the existence of markets for secondary materials, the cost-effectiveness of recovery, the project duration, and the contractor's experience. Countries such as China, Australia, Japan, USA, Germany, and the United Kingdom have successfully recovered numerous materials, for instance, paper, plastic, metals, and glass. However, Germany has the highest recovery rates for paper, plastic, metals, and 88% for glass, respectively. Tam and Tam, 2006. Tam and Tam, 2006, noted that the reuse and recycling of material waste are the only options to recover the generated waste. The benefits of recovering construction materials are summarized by USPA, 2000, as, reducing the project costs through avoided disposal costs, reduction in purchases of new materials, revenue earned from secondary material sales, compliance with state and local regulations, such as disposal bans and recycling goals, raising the public image of companies, and reserving space in existing landfills. In the context of material waste recovery, the word reuse was mostly used to signify the salvage or rescue of building materials for subsequent resale and use in another project. Winkler, 2010. However, if waste generation could not be prevented or minimized to a certain degree, the subsequent stage was to reuse or recycle, as much as possible. Eason and Koskun, 2007. Apart from prevention and minimization, most countries use this approach to reduce construction waste on site, before disposing the waste to landfills. Wang and Li, 2011. The Siemens company in Germany uses a very advanced waste handling technology for the reuse of construction materials. The process includes drying, distillation and burning to enable the waste material to be reused. Wang and Li, 2011. In Hong Kong, the sorting process of waste materials is common among the construction practitioners, and this action promotes the reuse of some of the generated waste. Poon et al., 2004. Consequently, a trip ticket scheme in Hong Kong encourages the separation of inert waste for possible reuse. Nagapan et al., 2012. Benefits of circular economy in construction. The global increase in the rate of material waste generation has led to the practice of recycling to become reusable. Mueller, 2012. Winkler, 2010, added that as raw materials are becoming more expensive and scarcer, and municipalities are resisting landfill extensions, so, the practice of waste management becomes more economical and important. Therefore, policy makers and construction managers must select which recycling practices to implement from the available options, in order to best divert material waste from going to landfills. Mueller, 2012. The benefits of the CE include economic, environmental and social advantages, and various authors argue that it is a sustainable approach. Economic benefit. Literatures in all the approaches under analysis claim substantive financial profits when moving from linear to circular production. Linder and Williander, 2017, Garza-Reyes et al., 2016, Lair et al., 2013, Liu et al., 2012. This is an unanimously claimed result of value creation. Nasser et al., 2017, Aitken and Harrison, 2013, Kabongo and Boyerl, 2011. Value creation results, on the one hand, thus reduce costs. Moreno et al., 2015. Those costs may be lessened from reduced marginal costs. Liu et al., 2012, reduced costs of buying virgin materials. Lair et al., 2013, reduced waste disposal. Esmali et al., 2015, or from lower environmental taxes. Anctil and L. E. Blanc, 2015, Paquin et al., 2015. Value creation can also be addressed from the other perspective of enhancing profits. Increased revenues result from exchange flows, selling waste as input for another industry. Lair et al., 2013, Gen et al., 2012, generating energy out of waste. Javana et al., 2012, or increasing brand and reputation effects. Tagnetti et al., 2015. An increase in market share and reduced risks is also mentioned by the literature in Closed Loops. Alblas et al., 2014. Preston, 2012, has asserted that the CE could assist in the industrialization of developing countries and reduce the vulnerability to resource price shocks in developed countries. Kier et al., 016, found that recycling, repair, reconditioning and remanufacturing improve profitability, but only reconditioning and remanufacturing improve sales growth. Paquin et al., 2015, used secondary data from 313 waste exchanges in the UK shows positive results in terms of eco-efficiency, as a reduction in waste also increased firm-level value through additional income and cost reductions. Values created, however, depended on the experience of the firm with industrial symbiosis, the volume of waste transacted, and the involvement of waste-dedicated firms. Environmental benefits. Most cited environmental benefits for all the CE practices include reduction in the use of raw materials, Fracassi et al., 2017, Linder and Williander, 2017, Esmali et al., 2015, Chowdhury et al., 2015, Paquin et al., 2015, and the minimization of waste, Kahka Anan et al., 2015, Chilshi et al., 2016, Garzarayas et al., 2016, HSU et al., 2013, Minor and Kiesma A1 Forthler, 2012. Reductions in carbon and greenhouse gases emissions are also claimed, Chowdhury et al., 2015, Esmali et al., 2015, with several mathematical models showing that products from nonlinear production processes have significantly lower carbon emissions during their life cycle than products made with linear production, Nasser et al., 2017, Hazen et al., 2016, Zalekian et al., 2016. Studies in energy use reduction are also frequent. Positive impacts have been found for closed loop, Zalekian et al., 2016, Industrial Ecology, Chertow and Miyata 2011, and Industrial Symbiosis Practices, Fracassi et al., 2017, Paquin et al., 2015. According to Gen et al., 2012, the potential environmental benefits of the CE are numerous, and include, conservation of natural resources, especially non-renewable resources such as water, fossil fuels and minerals, reduced environment impacts through efficient energy and material and less water discharge, avoidance of toxic materials, extended life cycle of landfill sites, and recovery of local ecosystem. Similarly, Jun and Xiang, 2011, revealed that the CE is expected to conserve resources and provide adequate environmental protection. While Gazellanyet al., 2016, claims that the objective of the CE was to split environmental pressure from a thriving economy. The CE model is expected to reduce unsustainable pressure on natural resources, which will reduce environmental challenges. Preston, 2012, Zhu et al., 2010. Social benefits. Murray et al., 2015, observes of the three pillars of sustainability, social, economic, and environmental, it is the former that is least expanded in most of the conceptualizations and applications of the CE. Employment and community development are the main social impacts analyzed. 3 studies factored in social welfare in closed-loop and reverse logistics modeling, Wang and Hansen, 2016, Zalekian et al., 2016, Pishvi et al., 2014. Wang and Hansen, 2016, finds that increasing government incentives and penalties over the closed-loop supply chain leader, either the manufacturer or the waste collector, enhances social welfare. Gen et al., 2012, have identified its potential social benefits, including improved relationships between local societies and industrial sectors, improved public awareness of environmental issues and health benefits, as well as employment opportunities from recycling businesses. Andrews, 2015, has emphasized that the CE creates employment opportunities for design graduates and professionals with related expertise across all industries. He notes that the CE has the potential to reduce unethical practices and corruption in the industry. It is expected to facilitate the selection of ethical suppliers while encouraging others to change. Andrews, 2015. UNETAL, 2006, has added that it could reform environmental management and create opportunities for collaboration between consumers and producers that will prolong commercial relationships between them. Similarly, Moreno et al., 2015, have supported the claim of UNETAL, 2006, adding societal benefits to the list of benefits. With the CE, national security will be strengthened owing to increased sustainable energy supplies. Suet al., 2013. Zhaijun and Nailing, 2007, acknowledge the potential social impacts of the CE to integrate populations, close income gaps, promote social justice and prevent environmental poverty. Pish vet al., 2014, compared the environmental and social impacts of supply chains with the recycling of waste and supply chains with landfilling. They evaluated social impact considering local development, created job opportunities, consumer risk, and worker health and safety. They found that supply chains with recycling not only have higher costs but also higher environmental and social benefits. However, they did not analyze more advanced nonlinear production options such as remanufacturing. Paquin et al., 2015, use secondary data from 313 waste exchanges in the UK to show positive results in terms of eco-development, defined as an increase in employment with a decrease in carbon emissions. They observe that the involvement of waste specialists, green logistics firms, in closed-loop supply chains significantly increases the social benefits of industrial symbiosis but at the expense of decreasing the economic gains of manufacturers. 5.0 Conclusion. This study reviewed the concept of circular economy, CE, its definition, principles, and benefits to cost in the Nigerian construction industry. And it also reviewed the construction industry, construction material waste situation, construction waste recovery systems and waste management policies in Nigeria. The key findings from the review are the three pillars of circular economy: sustainability, economic, environmental, and social benefits, and how they add value directly to the construction industry in the worldwide perspective, and how it can potentially add value to the Nigerian construction industry if and when wholly applied, and enforced by policymakers such as the government. To encourage greater implementation of circular economy principles throughout the supply chain, a clear economic case is paramount, and supported by metrics, tools, and guidance. The support from government through the regulatory agencies such as COREN, in the case of Nigeria, is very important.